Thank you very much for the kind introduction, and I also like to thank Jim for the opportunity to be here. This is my first time at this symposium, and it's been fantastic, extremely stimulating. And also the first we met. Oh yeah, and in terms of we've been in email contact since I think our first paper related to photosystem 2. I think within 15 minutes of that paper becoming public, I got an email from you. I'm not going to say if you're excited about it or if you're actually correcting us on aspects of it.
I was excited by it.
Okay, good. So my group has been focused on developing synthetic methodologies that allow us to perform structure function studies related to the oxygen evolving complex in photosystem 2. We really think that if we are to take the problem from its natural environment, the protein environment, and change the ligands and change the second coordination sphere and so forth, we really have to come up with ways that will allow us to make structures that are really very much related structurally one to the next. Otherwise, we're not going to be able to perform structure function studies. If you change too many aspects of the complex, it will be hard to come up with conclusions. But of course, the questions we're interested in addressing have been discussed over the last day or so related to the function of the redox inactive metal calcium, the reactivity of terminal and bridging oxos in clusters of this complexity, the effect of remote metals, remote from the site of O bond formation, as well as questions related to second coordination sphere and the transfers of protons and electrons. I'd like to note, as Holger Dow mentioned in the previous talk, that there are also heterogeneous metal oxides that have calcium and manganese and have been reported to present structural motifs very much similar to the one in photosystem 2. So our hope and hypothesis has been that if we come up with methods to synthesize structural motifs similar to the one in the biological systems, they may teach us something about the artificial catalyst for water oxidation as well. And so what's our approach, right? So if we start from the full cluster here, I'm just focusing on the metals and the oxygen bridges, as well as I'm adding a terminal ligand on the dangler here. We like to be able to dissect this cluster in multiple ways to address questions about the reactivity of different structural motifs, right? So we talk about the cubane. Can we make versions of synthetic versions of the biological system that focuses on the cubane? And of course, the dangler has been invoked in many proposals for O bond formation. Can we make clusters that have that motif as well, and perhaps the ability to bind or to support a terminal oxo moiety specifically at that position. And so these are the type of structural motifs we're targeting, and we like to target them in a way that will allow us to have atomic control. We really like to be able to say and apply, change a specific atom in that cluster and see how that affects the properties of the cluster. And of course, that's a challenging problem in terms of synthetic chemistry. I think of this as a total synthesis in inorganic chemistry. And so in terms of approach to go from a precursor, we think that starting from a trinuclear manganese cluster and then building from there to add a calcium to make a calcium cubane, and then from there attaching a dangler will allow us a control of the structure and changing the nature of the metals so that we can perform structure function studies. We've developed a ligand framework that allows us to selectively make a trinuclear precursor. That works very well, and then starting from the trimanganese precursors, the trimanganese 2 species, if we add calcium triflate as the source of the fourth metal and superoxide as the source of oxygen and oxidizing equivalents, indeed we can make a calcium trimanganese tetraoxocubane. And if you look at the crystal structure of this motif, it really maps very well onto the cluster of the cubane substrate of the oxygen evolving complex. So we're very excited about this early result towards modeling this heterometallic cluster. But really, I think the most important part of this methodology is the fact that we can change the calcium to other metals. and so to really address the question of the role of that redox inactive metal. And so, for example, we can start from the calcium trimanganese tetraoxocubane and add a source of a more Lewis acidic metal that's redox inactive at these potentials. I'm showing scandium here to make the corresponding scandium trimanganese tetraoxocubane. So in terms of the structure of the cubane, we're really just changing one atom. Calcium for scandium. And we can do that with a variety of metals. I'm showing here a subset of the compounds we've made. And you can see that as you move from calcium and strontium to zinc, yttrium, scandium, and so forth, the reduction potential of this cubane cluster is affected dramatically, actually over 1 volt. Okay? I'm not going to get into the details of how we made a variety of other clusters, but I'm going to present this plot here to summarize what we found. So this plot shows the reduction potential of the clusters as a function of a measure of the Lewis acidity of the top metal here, metal M. Okay, and so that's here is the pK of the metal aqua. If we use other measures of Lewis acidity, we get similar plots. Okay, and so if you look at the cubane here, you see how the reduction potential trends linearly with the Lewis acidity of the top metal. Okay, and so that gives us the chemical basis for how the reduction potential of the cluster, which changes at the manganese, is affected by the redox inactive metal up top. And we see a similar linear trend for clusters that don't even have manganese. This is a triiron M oxohydroxyl species, as well as for clusters that have 3 manganese centers but are only dioxo. So this is really a general phenomenon that shows how the redox chemistry at manganese is affected by redox inactive metals. Another important aspect in this plot is that the calcium and strontium are always together for their respective structural motifs. And this correlates back to the observed behavior of photosystem 2, where calcium and strontium are really the only ones that are capable of doing oxygen evolution. Right? So we see here that the reduction potentials of these clusters are very similar. Okay? And so this, to us, suggested that the role of calcium and strontium in the biological system is to tune the potential of the OEC to allow it, if you look at where the potentials are here, to allow it to get to the high oxidation states necessary for OO bond formation. Of course, the actual potentials will be different because we have other ligands. We don't have all carboxylates, right? We have alkoxides and pyridines and so forth. But in terms of, because we have a structure function studies that allows us to say something about the cluster as we change different metals, I think a similar phenomenon will apply to a biological system. I'd also like to note here, because it came up in talks yesterday, our studies of ligand and label, isotopic label incorporation into different types of cubane moieties. So I'm showing here a tetramanganese trioxocubane, and so this is somewhat reminiscent of the open cubane motif in the biological system. I have a tetramanganese tetraoxocubane, and I have the calcium trimanganese tetraoxocubane. And we've looked at acetate exchange. These are mass spec studies looking at how labeled acetate incorporates into the cluster. And we find that when we have only manganese 4, that exchange is very slow, which is what you expect for a D3 system. When we have a cubane moiety, but with manganese 3, despite the fact that we also have manganese 4, that exchange is fast. Now, if we look at oxide or water incorporation, the calcium trimanganese cubane, all manganese 4, very fast, very slow exchange as you'd expect. Same applies for the tetramanganese tetraoxocubane, despite having manganese 3 around. And so these mu3 oxo moieties are actually very slow at exchanging. However, when we have an open cubane like this one, and we add water under oxidative conditions of ferrocenium, not a strong oxidant, we actually do see oxide incorporation from the water. And so I guess thinking back about what happens in photosystem 2, given the proposal of the open cubane, one could imagine in that case that the water could perhaps incorporate fast, but we are not addressing with these experiments that particular case for the S3 states when everything is manganese 4, right? We have the example for manganese 3. And so related to the proposal that there are two isomers that open and close cubane, we do see the scrambling of oxo moieties within our clusters, although I'm not showing here the experimental details. Okay. And so more recently, we've been interested in changing the nature of the ligands around these cubanes to access higher oxidation states corresponding to the S2, S3, perhaps beyond that, states of photosystem 2. And so we changed the acetate ligands to amidate ligands. And so if you think about the pKs of these ligands, we go, the difference about 10 pK units per acetate or carboxylate to amidate. And as you expect, when you make the cluster more electron rich, you do find that the cluster is easier to oxidize. So you see here the difference is about 350 millivolts. And so we're interested in doing the same with the heterometallic cubanes. And so we did this with the yttrium version. And just to increase the stability of the cluster, we actually used a tris amidate that is chelating through this nitrogen up top. This is a so-called trend type ligand. And we're actually very surprised to see an opposite effect. Okay? If you look at the reduction potentials up top, we go from 250 to minus 100 millivolts, while at the bottom we go to from minus 430 to minus 290. So we're moving into the positive direction, despite having much more electron-rich ligands. And so that was very puzzling to us, and it's something that we're continuing to investigate. But what we're hypothesizing right now is that the ligand, there is a ligand pressure because we have this chelate up top, which enforces the yttrium to come closer to the oxo moieties and essentially to the manganese centers, which results in a positive shift in the potential. Now the cluster is harder to oxidize. And we see structurally that the yttrium oxo distance is decreased by 0.1 angstroms in the chelated version relative to the acetate analog. So I have become very interested in understanding how the protein structure puts pressure on the cluster, right? You could imagine the cavity being pushed on by the ligands. Of course, so ligands, it's a cavity, right? Ligands come from everywhere from the protein. Unlike in our system where initially we had it from the bottom and the acetates were just accommodating what the metals wanted. Once we added the chelate, we're putting pressure from the top, if you will. But you could also imagine the protein structure putting outward pressures, right? Where the carboxylates are just a little bit further out than the manganese would like to be. And I think that might have substantial effects on the electronic structure and reduction potential and so forth. And I think we probably already have all the data given the structural characterizations that have been reported over the last decade. And so going back to why we're making these more electron-rich clusters, I have here the tetramanganese tetraoxocubane that I described a few slides ago. And so it doesn't have the structure that's now accepted in terms of the oxygen evolving complex, right? It's a closed cubane with 4 manganese centers. However, if you look at the EPR data on this cluster relative to the oxygen evolving complex, you'll see that there's great similarity. And again, to us, this was a bit surprising. And of course, I'm not, given the data that's available in the literature, I'm not arguing that in the biological system we have a tetramanganese tetraoxocubane. But I do see it as a warning sign in terms of the types of structures that one might generate in solution that may have spectroscopic signatures very similar to the biological system. And one has to be careful about the conclusions that are derived from those spectra. Nevertheless, in our case here, we are, I think, in a great position to, again, perform structure spectroscopy studies to understand how distorting these cubanes electronically as well as structurally affects the population of these states. So I should have said here, we don't think of these as two isomers. They're really the ground state, low spin and high spin excited state of one cluster. Okay?
Theo, can I interrupt you? When you say cubane, is it a calcium 3 manganese cubane or is it a 4 manganese?
So these are 4 manganese centers.
Right, it's just the manganese 4 over
That's right. It has, but it has the oxidation state that we know from the preparation and the crystal structure that has the right redox state for the S2. And as you can see, spectroscopically, it matches very well for both for the high spin and low spin signals.
Which essentially means that characteristic is spin interaction under those particular oxidizing conditions, isn't it?
So, well, it means that I guess coincidentally, you may get to the same spin interactions as observed in the oxygen evolving complex. This is how I would put it, I guess, conservatively.
Any conformational changes, two different structures, a closed structure and open structure, I think it's been suggested.
That's right. So that's the proposal in the literature, and I'm showing that with the
You
cubane.
wash that one out, I think, don't you? Well, you don't like to say, but I can. Okay.
That's your saying. I did not say that, for the record.
I totally interrupt you.
All right, so I'm just showing here an example where you have amidate versus carboxylate, and you can see how this feature here is affected to some extent, and we're interested in making further versions of these compounds. And so related to what Dave Britt was mentioning in his talk this morning, we're looking forward to collaborating with him to access a model of the S3 state. So we have the EPR here. Unfortunately, we don't have structural data to confirm that we still maintain the structure that I'm drawing here. And so the focus so far has been on the cubane moiety. We've worked towards taking the calcium trimanganese tetraoxocubane and desymmetrizing that. So in our initial system, it's high symmetry, pseudo C3 symmetric. If we add this ligand that's emphasized up top here, essentially we're adding a belt around calcium. We find that the stability of the cluster increases significantly. It turns out that we just acetate, calcium simply displaces, manganese simply displaces the calcium. If you have donors from the top, which is reminiscent of what you find in the protein, that is not the case, and we've been able to make compounds that have this dangling silver moiety that maps onto the tetramanganese on the oxygen evolving complex structure quite well. And so I think over the last decade or so, we've seen quite a bit of development in terms of models of the oxygen evolving complex from Christos, calcium trimanganese oxocubanes that are part of more complex clusters, 15 metal centers, to our cubane. Then Christo reported a calcium dangler. We reported a silver dangler, and then most recently the Zhang group reported a manganese dangler. And so I'm very excited about being part of this development, and I'm hoping that, at least from my perspective, we'll be able to further develop the methodology to allow us for systematic structure function studies related to these motifs. I like to change gears now to the other way we dissect this cluster and tell you about our models that now focus or incorporate the dangler as part of the tetrametallic motif. The clusters I've described so far all have metal centers that are six-cornered. And in all those cases, we did not see water oxidation catalysis. Maybe I should rephrase that. All of those systems can do water oxidation if you go positive enough in potential, because at some point you're going to get manganese oxides that precipitate on the electrode. But in none of them, we've been able to make systems where we could say confidently that the chemistry happens with the actual cluster and it's the homogeneous system that performs water oxidation. And so we thought that a model of this dangler moiety was necessary for water oxidation. Moreover, we want to make a system that allows, had coordination sites available for water binding and oxo support. And so we came up with this type of strategy where we like to bind or to come up with a way to install an oxo at this axial position. And we also have these three metal centers that are not directly interacting with that oxo moiety. And we thought that could give us insight into how remote metals in clusters of this complexity affect reactivity. And so if you go back to the structure of the oxygen evolving complex, of course, it's not only the metal centers and the bridging oxo ligands, but it's also the second coordination sphere that may affect reactivity. And so we're actually able to design a system that has hydrogen bonding interactions coming to that position where we support a metal oxo or hydroxide or aqua. While ligands of that type have been developed previously, they've been popularized by Andy Borovic in terms of oxygen evolving complex. They have been used for monometallic systems. And so we're interested in developing a version that allows the support of multimetallic systems. And so again, starting from our trimanganese precursor, we can access tetramanganese monoxo hydroxo clusters as well as chloride clusters. And if you look at the crystal structures in these systems, you see that, for example, with the chloride, we have 3 dative hydrogen bonding interactions with the 3 lone pairs on the chloride. And with the hydroxide, we have 2 dative hydrogen bonding interactions to the hydroxide and 1 acceptor to this moiety here. Really structurally mimicking aspects of second coordination sphere for terminal hydroxide moieties related to oxygen evolving complex. And perhaps the more exciting aspect of this chemistry is that once we do electrochemistry and we titrate in water, right, the substrate, these are soluble in organic solvents. We start water-free and we keep adding water. You see an increase in current at positive potentials, suggestive of water oxidation catalysis. And it turns out that we don't go all the way to dioxygen. We make hydrogen peroxide in this system, but we're excited about the fact that we can make all bonds. And all our control experiments really are consistent with water oxidation by this homogeneous cluster. And it turns out that the yields are fairly low, and that's because part of the electrons go to not OO bond formation, but CH activation of the organic solvents, and then we can quantify that to a good extent. And so now we have a demonstration of a system that mimics part of the oxygen evolving complex, including the dangler, and also shows some function in terms of OO bond formation. And we're very interested in understanding the nature of that of this ligand up top here as a function of the composition and structure of the cluster. And we really had to come up with a trick there to be able to address the oxidation state and the nature of the metals at the 2 different positions, right? We have a metal up top that binds the water and the hydroxide ligand, and then the remote metals. And if all of those are manganese, it's hard to understand how they talk to each other. So we decided to make a heterometallic version where the metals at the bottom are iron and the metal up top is manganese, right? So then we can use X-ray techniques to selectively learn about the manganese and the iron. We can use Mossbauer to selectively learn about the iron centers, okay? And then we have structural characterization for the aqua ligand as well as the hydroxide ligand. And this is the electrochemistry for the aqua ligand as well as the hydroxide-based clusters. And so taking all this information together, now we can look at proton-coupled electron transfer in these systems, addressing the question of how these remote metals affect the properties of the aqua and the hydroxide ligands, okay? And so I'm not going to go through all the details here, but I like to just to emphasize the fact that over 2 oxidation state changes in the terms of aqua ligands and 3 in the terms of hydroxide ligands, the manganese up top doesn't change, right? In all of these cases, we have a manganese 2 aqua being deprotonated to, or losing a hydrogen atom, going to a manganese 3 aqua, right? So in terms of comparing to monometallic precedent from inorganic chemistry, all of these are the same, right? But it is clear from our studies that the cluster structure really has a significant effect on those aqua and hydroxide ligands. And I can emphasize here the bond dissociation energies of this OH moiety. As we increase the oxidation state, we increase the bond strength by about 10 kcal per mole. despite the fact that the manganese center remains the same, right? It's just that the remote metal iron, which we can investigate independently, has a substantial effect on the chemistry of manganese. And this, of course, relates back to photosystem 2 in terms of the fact that we have a cluster there, and chemistry happens at the cluster, and the remote manganese centers have an effect on the properties of those oxo moieties, and the chemistry does not happen at just the mono manganese center. Okay, and we've been able to map this onto a Pourbet diagram, and from these Pourbet diagrams, although we haven't isolated the corresponding manganese oxo species, we can tell that they are very reactive. And so the lower limit for the BDE to access a manganese oxo moiety in some cases is higher than 100 kcal per mole. And so those oxos are expected to be very reactive, which is what, of course, you might expect for all bond formation reactivity. Okay. So I'll just briefly here point out to a different strategy that we've been approaching to access the terminal manganese oxo. Instead of adding water and deprotonating, we can transfer oxygen atoms from iodosobenzene. And we find that we're generating very reactive intermediates. So we see for the tetrairon cluster, we see CH bond activation. A typical way to avoid that is to substitute those ortho hydrogens with fluorides. And so we would perform the substitutions, and we actually see CF bond activation. There are very few examples of such reactivity, again telling us that the species that we're generating, this metal oxo intermediate, is very reactive. And similar reactivity happens with a corresponding tetramanganese cluster. And so again, we're performing studies related to what I described earlier, where we have a manganese up top, 3 irons at the bottom, and looking at lower temperatures to access, hopefully, and be able to characterize metal oxo species, and to understand how the reactivity is affected by the oxidation state of remote metals, as well as the nature of those remote metals. Okay, and so I'll summarize here by saying that hopefully I've convinced you that being able to have access to synthesis where we really have atomic control on the structure of the cluster really has allowed us to learn a lot about the effect of structure and different metal sites on reactivity, on the redox chemistry, as well as the spectroscopy of these mimics of the oxygen evolving complex. I'd like to thank the people who've been involved in this work. Primarily the people here in red have contributed to the work described today. Our collaborators, in particular Junko Yano and Dave Britt on XAS and EPR, and NIH for funding, and you for your attention.
Thanks very much, Theo. That was a great talk, and also thanks for staying right on time. We have some time for questions now. So maybe I could lead off with one. I have a lot of more technical inorganic questions, but one maybe more general question that the audience might be interested in. You made the comment about the manganese 3 open cubane being very labile for ligand exchange, and that the manganese 4 cluster was inert. But then you sort of alluded to the possibility that if you had an open all manganese 4 cluster, there might be exchange. Maybe I'd ask, could you elaborate on that, why you think how that might work?
I guess I just left the door open there, that could still be a possibility. We just don't have the experimental data to go one way or another. What I can say is that once you have a closed cubane, with a combination of manganese 3 and manganese 4, those oxos don't seem to exchange. Right. Okay. And so if I keep that and say, okay, now I go to all manganese 4, they should still not exchange, right? And we see that with the calcium trimanganese. Now, if I distort the cubane, I don't know. Yeah. But if you have an open coordination site, I can see, that arrives there because of other distortions. I can see how water could
In
exchange.
general, though, you'd expect an octahedral manganese 4, which is high spin D3, should be very substitutionally inert.
No
And-
reason to exchange.
Yeah,
Absolutely no.
and-
Extremely slow, right?
And you'd suit that with the terminal acetate ligands. They
That's
don't
right.
exchange.
That's right.
So,
Yeah, so it doesn't.
It's
so
not clear to me that if you had an open structure that you would promote any kind of exchange in that with an all manganese 4 cluster.
Yeah, so manganese 4, right? The oxo ligands, I mean, they have 3 metals coordinated to them, right? Even just the acetate by itself, right, which is a terminal ligand, is very slow at exchanging. And so the bridging one, that much slower, I would say.
Yeah, yeah.
I don't.
Can we just say that when you're in a higher oxidation state, that the cubane is robust and stable?
It's not necessarily just the oxidation state. Manganese 4, right, is D3. There's no population of sigma antibonding orbitals, right? So there's no weakening of antibonding of bonds because of that.
Yes, of course.
And so the exchange kinetics is very slow.
Because mechanisms are being suggested, as you well know, that the structure can open up and allow, say, a water molecule to be engulfed or exchange. Does that seem likely to you from your... No, you're not going to answer. You're too young and too worried about it.
I'm not worried about it. I think I can see how you know, if for whatever reasons the clusters are distorted, maybe exchange will happen. Now I don't know why the cluster gets distorted.
Not by any other ion. There's no ion there. There's nothing else. It's just protein.
I get from an inorganic perspective, if it's perfectly octahedral geometry, you'd expect very slow exchange, no matter whether it's open or closed.
Yeah.
But if the geometry is being distorted away from an octahedral geometry, then you can perhaps promote more rapid exchange. I think that's
Yeah. So if you get to a 5-coordinate manganese 4, for whatever reason, this distortion, right? Some of the structures presented, right, have essentially an open coordination site.
Yes, yes. What will
You
be
could
the
imagine.
energy demand to make those sort of changes? There will be energy involved in making the conformational changes. What level? would that be?
That's a hard one to answer because you're not just breaking that bond, right? There are other, at least all of the proposals put out there, there are other bonds that are being formed
Yes.
to compensate for that, right? So
In the
it's
end
a
of the
tough
day,
one.
When you have large structural changes, there will be an energy consumption. There may be compensations and so on, so it's difficult to work out. And on the other hand, the over potential for OO bond formation in photosystem 2 is quite small. As our friend Jerry Babcock used to say, who didn't know, which is a pity, but it's on the thermodynamic edge, he
Yeah.
used to say.
Yeah, I think maybe we can move on to the next question, but one thing that might be of interest to the structural people looking at photosystem 2 is to look carefully at the coordination geometry of each of the manganese in the S3 state, because I think that will be informative about whether these kind of distortions are happening. You know, that's going to be relevant.
yeah, and I'm very much interested in what type of pressures the protein puts on that cluster.
Yeah.
I think I haven't seen discussions of those sort
Yeah.
in the
Yeah, I
papers
think
out there.
The structure in particular of the S3 state is still emerging. We need, that's a hard state to get a high resolution
I'd say
structure.
this, that you can do a lot of mutations of the ligands in the first coordination sphere and not really see a lot of change. There's some of them you see no change. So it's quite tolerant to changes in the protein environment.
Yeah. Let's go on to Li Chen.
Okay, so I want to try to confirm with you. All the synthetic models based on tetrameric manganese that matter with calcium or screnium does not show any water oxidation activity if applied potential below, let's say, 1.2 volt. Is that true, including yours?
Well,
If you apply a little higher, of course, you get manganese oxide. That shows activity, but
well, so the tetramanganese, so not the cubane, but the tetramanganese that I showed, right, that has a mu4 oxo, that does show water oxidation.
okay.
Okay, and then there are examples in the literature of cobalt cubanes that do.
I'm thinking the
Well,
manganese.
so this MUX has some tetramanganese cubanes as well, although there have been debates about.
I think they have
It's a
to
real
break, they have
catalyst,
to
yeah.
break before you see activity.
Well,
Yeah,
that has been going back and forth, and I don't want to get into the middle of that. I haven't run the experiments myself, and there's debate in the literature. I'll leave it
Okay.
at that.
Right here.
Yes, it's nice talk. I would like to ask about the ligand change. You said you get different coupon with different mechanisms. You get the redox potential difference. But you also recently you also report the ligand change on the for example atrium or the calcium. Actually that make also the redox potential of obvious change. So I'm wondering, because all your model complex, actually the redox potential, just Professor Sun just asked about the redox potential is very low. So that means it's just related to the coupon or the ligand. Main contribution come from the ligand or just the coupon.
Well, so we're not. So if we have just made one cluster, right, the calcium cubane in isolation, right, I don't think we could have said anything about how that relates to the biological system, right? Because it's one data point, and it's taken out of the protein matrix, but we keep all the ligands the same, and we're just changing the top metal. Now, it's true that the reduction potentials we have, right, are going to be different, and we show that they're different relative to other clusters we're making. But within that structure function study, where we're really just changing one atom at a time, we see those linear correlations, okay? And so what I'm proposing is that if we were to do that change systematically for more complicated clusters, when we have a dangler, or even beyond that, again, you'll see a linear trend as long as you keep the structure the same. Of course, things in the biological system, there's the dynamics of that's been discussed over and over again here, how that will affect reduction potentials. If for one metal you see the equilibrium in between those two structures versus one you don't, that I can't address at this point, but I would expect, because you get a different cluster structure, that they might not be on that line.
So actually,
Because you change the structure.
I would like to ask if you change all the periods, because you have 6 periods in your ligands. If you
Three
all these
bound to those cubanes.
Yes.
Yeah.
Yes. So if you change the ligand from nitrogen to oxygen, what will happen?
It depends. I would expect it. I mean, we haven't done that exact experiment, but if we go to an anionic oxygen, I would expect to move the potential so that the cluster is more easily oxidized.
Yeah, actually,
Let's move on. So one last question, and we need to get to the coffee break. So
Is there a technical reason that the chemists of the older times, like Pecoraro and Vicard, who would really have loved to produce these constructs, could not, and now you and Zhang and others can?
Part of it is how the field has evolved, right? I mean, we didn't have the structure that we have right now, right? 20 years ago, right?
Oh,
no.
With gyms, it was at least
So that's-
When we suggested that structure, there was nothing in the chemical.
Right. So this is 15 years ago, right?
Nobody had looked at manganese calcium complexes. The first person to do it was Kustu, it was mentioned here. And they took some calcium, they took some manganese, the appropriate anions, and they added oxygen, and they shook it around a bit, and they ended up with that structure that you saw there, which there were 2 building blocks in the structure, macroscopic.
So that's a manganese 11 calcium 4 cluster, right? That's
Yeah.
from 20.
And there were 2 building blocks only in there that made up this macromolecule. One of them was exactly like photosystem 2, which was the asymmetric cubane with the dangler manganese, and then they also had a M4O4 cube with a calcium dangling. That was the whole basic 2 building blocks. And that was really the first evidence of this type of molecule. Could it exist? I think that's true.
So if I'm to follow that, the challenge is having the right ratio of the 2 metals and stopping at the right cluster site, right? Oxoligands are very good at bridging, and we don't have the constraint of a protein cavity. And so you have, you get complicated structures like Christo reported earlier. But now with the type of structural data we have, we know exactly what we need to target. But you still have to control the asymmetry of the cluster and the distortions in it.
When people were being very critical of the structure that we suggested, I used to, you probably can't remember the lecture, I used to give the example of Christo, because paper is 2005, and George came and saw me many times, but, and that was very important to me that they saw that unit in that macromolecular system, because then I knew that it existed, and it's remarkably similar in dimension, and geometry is the same as the photosystem too. Absolutely amazing.
Okay, let's wrap up this session. Let's thank Theo and all the other speakers again.